Swayam Prabha. Digital India. Educated India.
Welcome to the class of high performance computing for scientists and engineers. We are in the second module, which is OpenMP programming, and we are discussing essentials of OpenMP programs. This is the second discussion on essentials of OpenMP programming. In the previous lecture, we covered the concepts on OpenMP environment routines and the directives and constructs of OpenMP, and we have especially focused on parallel directives in OpenMP, and inside the parallel construct we can use other constructs like OMP4, etc. We have looked into that. Previously we have also discussed about different type of variables in OpenMP and shared and private data, how data handling is taken care in OpenMP. So, look into the remaining important aspects, which are work sharing, reduction clause and scheduling, and also nested parallelism in OpenMP. And the idea is that once we are aware of this particular semantics and syntaxes of OpenMP programming, and also the functionality of different OpenMP constructs and clause, will be able to develop our own OpenMP program. Some of them we will see in the subsequent classes. So, we are actually discussing on work sharing directives in OpenMP. We have earlier seen that whenever we need to do something in parallel in OpenMP, the first important directive is hash pragma OMP parallel, or in Fortran Sentinel OMP parallel. That specifies that the construct which has been the construct means directive and the associated clause, and the associated code block. The construct which has been launched in the OpenMP program, this construct will work in a parallel mode. That means multiple threads will be active, and these threads will take care of the remaining part of the calculations, and some of these threads will work in parallel. Depending on the number of processors, the threads will work in parallel. And now, what will these threads do when they are launched in parallel? There can be certain cases, because OpenMP is specifically designed for some class of computation, which are we generally call them scientific computation, which we are discussing here. So, it is a priori known to the developers that these are the type of programs, or these are the type of algorithms that OpenMP is trying to parallelize. And what are the region of the program which requires parallelism? One part may be that there is an iteration. There are a number of iterations. There is a do loop or a for loop which will take care of number of iteration, and these iterations are mutually independent. That means for I is equal to 1, the calculation is independent for I is equal to 10, the calculation in the same loop. So, this do loop can be parallelized. The other issue can be that there are different tasks, and these tasks can work concurrently. These are not most likely part of what I will say part of a same iteration loop, but there can be tasks. Say for example, we are looking into solving some equations of motion, and equation of motion in x direction and equation of motion in y direction and in z direction are independent of each other, because the acceleration that we will get from the force, and as force is equal to acceleration into momentum. So, if you know the force and mass, the acceleration you will calculate there can be independently calculated in each direction. So, in order to calculate acceleration in each direction, independent threads can be launched. So, the second part of parallelism can be that there are independent works but at one instance you want to know the acceleration in all three directions, at the next instance you again need to know acceleration in all three directions. So, there can be independent works which are large pieces of works, but they will be probably repeatedly solved, and solution of each unit of this independent work will take certain amount of time. So, if we can launch multiple threads for this thing. So, if we can launch one thread for x axis calculation, one thread of y and another thread of z. So, this type of work distribution, that if we can identify that these are the sections of work which can be executed concurrently and launch different threads for them. So, within the parallel region we will say that now multiple threads will be there. So, these threads, each of the thread can look into different sections, and this is the next part of the next way of OpenMP parallelization, that is launching sections and distributing independent works. And then there can be another work sharing, that on a certain case we see that, so again we are discussing about solving momentum equation in x, y and z direction, and in certain case we see that there is no force, therefore no acceleration in y and z direction, we only need to calculate about x direction. So, we will not launch any thread in y and z direction. So, we will ask only one thread, though everything is in the parallel region, but we will ask only one thread to do that particular calculation. So, it is also possible that only one thread will execute that part of the code block, the other threads will not do that. When we will see this work sharing directives, we will appreciate the fact that when somebody is developing a parallel program, he is not developing, he is not writing instances for different threads, he is not writing different instances, or he is not writing different lines of the program for different threads. It is developed in with a sense of generality, that one particular line within a parallel region will be executed by all the threads, and these threads, they are operating something like a single instruction multiple data model. So, each of these threads will operate will execute the same instruction, but they will pick up the relevant data for their work. So, they will get connected to the relevant data, but they will essentially execute similar type of instruction for them. In case they have to do different instruction, which is multiple instruction multiple data, it can be also via section model, that different thread will do different work and pick up data differently. However, when the program is written, the programmer does not really try to write instance of the program specific to a thread. So, what is his role? Rather, to write it in a general format, and when these different threads are launched, each thread using the algorithm will pick up its relevant work and execute that. And therefore, if there is some work which is specifically to be done by one particular thread, we have to specify that other threads will be going inert mode and only one thread will do that. So, this is also one part of work sharing. There are other parts work sharing like pragma OMP master, when only the master thread or thread ID 0 will execute that block of code. So, you are controlling mode on that this particular thread will work here by pragma OMP master. There is another interesting construct, work sharing directive, which we will see later in detail, pragma OMP critical. It shows that though the works are independent and mutual threads are concurrently active, but at one particular region of the work, each of the thread will follow some sequentiality. So, one by one threads will do that. Not all the threads will try to attempt to execute that particular instance of the program at same point of time concurrently. And this is in particular done when you have a single shared memory variable and multiple threads will try to update that variable. So, you put OMP critical, that means one by one the threads can update the variable, so that there is no contention, no race condition, no overwriting of the shared memory, etc. This is also one important work sharing directive. So, look into little more detail. And so, one of the work sharing directive is a loop construct. That means, there is a do loop and you have parallelized this do loop using hash pragma OMP for or Sentinel OMP do in Fortran. The first one is in C. So, what is done here? So, if you see this particular Fortran code, we have a loop do I is equal to 1 to 8 ID inside the parallel. This is the parallel region of the program. So, let us see that this parallel private is the parallel directive, and we call the entire part, it starts at OMP parallel private. In Fortran, it is easy to identify end of the parallel construct by OMP end parallel. So, this entire part is called the construct. This entire part is the parallel construct. That means, at this region multiple threads are launched and they are active concurrently. And at the beginning we find out, sorry I just did a small mistake here. This entire part will be from OMP parallel, OMP end parallel. This entire part is the parallel construct. So, this is construct, we have seen it earlier, and this is called the this part is called the construct, and this particular line OMP parallel is called the directive. Well, now inside the construct, and there are 4 threads which are launched. 4 threads are launched. Inside the construct, first it finds out the ID of the thread. Each thread has different ID, and now there is a do loop, do I is equal to 1 to 8, IA is some variable which is ID plus I, and each of the thread will take care of some parts of this I loop, because we have launched OMP do, and this is another construct which starts at OMP do and ends at OMP end do. Within these 4 threads which are launched, so I will again highlight it. These 4 threads which are launched, these will take care of this 8 iterations, in the do loops 8 iterations. So, we will see the result in the right hand side later, we will see it later, we will see that how this has been taken care of. And what will they do? They will update a variable IA. What is IA? IA is a thread private variable. So, for each variable IA is each thread IA is somewhere private. IA is equal to ID plus I. I is the iteration number and ID is the thread number. So, for I is equal to 1, we can see, because there are 8 iterations which is distributed into 4 threads. Each of these threads, I is equal to 1 to 3 2, each of these threads are picking up, each of these threads are picking up 2 of the iterations. Thread 0 has picked up 1 2, thread 1 has picked up 3 and 4, thread 2 has picked up 5 and 6, thread 3 has picked up 7 and 8. Each of the threads have picked up 2 of the iterations, and what they have done, they have written that IA, which initially started from IA is equal to 0, Fortran initializes it automatically to be 0, I is equal to ID plus I. So, for thread 0, ID is 0, therefore, IA will be 0 plus I, the values of I. For thread 3, ID is 3, but I goes here at 7 and 8, last 2 iterations, and this they will pick up 7 plus 3 10 and 11. Well, so we can see that there are some iterations, and this number instead of 8 can be anything else. Also, the thread number could have been anything else. OpenMP compiler itself distributes different iterations to the number of threads, and here we can see there is an even distribution, that means there is a load balance distribution, but there are cases when the number of iterations is not exactly divisible by the number of threads. However, it ensures some sort of load balancing. Also, the programmer has some control over the distribution of threads, distribution of iterations over the threads through schedule clause. We will look into schedule clause later, but right now we can see that if we just see that there is a for loop, it is a do loop, there is a do loop in Fortran, and if we can just define OMP do construct, then this is automatically parallelized and distributed among threads. Well, so this is what is called a loop construct, and this the same thing will happen in Fortran. Iterations are mapped to the threads in the identical manner for all do loops. The number of iterations are, if the number of iterations are same, well, so we will come into it later. So then we will see that there is also another do loop, do I is equal to 1 to 8, same number of iterations, iterates updated IA is equal to I plus ID. What is the value of IA, that is again added with IA. And we can see here iteration 1 and 2 we are going to ID 0. Here also this is again same way parallelized. So, this loop ends, another loop starts here. This is also iteration 1 and 2 goes to ID 0. Iteration 7 and 8 going to ID 3, thread 3, iteration 7 and 8 here also goes to thread 3. So, the distribution of the or mapping of the iterations to the threads are identical for all do loops if the iteration numbers are same. If the iteration number changes, it happens differently, but this gives a very good control for the programmer over the work distribution in OpenMP, because he knows that these iterations, and if he is trying to solve something over a large number of iterations and the iterations happen over and over, he knows that these iterations are specifically assigned to this particular thread. Another point is that we have said that the variable IA is a thread private variable. So, the copy of IA remains in each thread at different do loops. What happens that what is the last updated value of IA from the first thread, ID is equal to 0, ID is equal to 0 has the values of I1 and 2, and the last updated value of IA is 2. So, this value 2 stays with the thread number is 0. With this thread 0, the value IA is equal to 2 stays, because it is a thread private variable, and it starts IA is equal to IA plus ID when it writes updated IA. That means this value 2 stays here, the value 2 comes here, 2 plus 0 is equal to 2. For thread 3, IA was 10 and 11. So, the last updated value was 11. This 11 value stays with thread 3. Now, at the next loop, thread 3 does IA is equal to IA plus ID. So, it is 11 plus 3 IA plus ID, 11 plus 3, and again it adds another 3, 11 because ID is 3 here, 11 plus 3 14, 14 plus 3 17. So, this stays here because they are thread private variables, these values stays with the thread. So, these are certain features of do looping and thread private variable. So, if the main point is that if there is any do loop in Fortran or for loop in C, if you use parallel for C, or if you use OMP do or parallel do for Fortran, it will be automatically parallelized, and some of the iterations will be mapped in the loop will be mapped to some of these threads, and this will be identical if the number of iterations remains same for same number of threads. This is same for C also. And we also can see if we write anything here after the end do loop or after finish of the first construct, first do parallel do construct is here, sorry. If we write anything after the end of the construct, this will be operated sequentially. That means this thread ends here, everything executed by all the threads finishes, and the next instances of the program are launched, and therefore, this is called an implicit barrier. That means all threads finish their work. In case some thread has not finished the work, the other threads will wait for it. Well, then another loop is launched, fine, and we can see that when the new loop is launched, the number of iterations specific to that is same, to that particular thread is same, and the updated value, the last updated value of IA, which is IA is equal to 11, goes to this thing. This is 11 plus 3 is equal to 14, and then 14 plus 3 is equal to 17. The value of the variable comes here as it is a thread private variable. Well, but and also we can see that this is same in C also. In C, that the loop construct is for hash pragma OMP for, you can parallelize the particular for loop using hash pragma OMP for, but this is important that this parallel do loops must be part of a parallel construct. They should follow a directive parallel OMP parallel or hash pragma OMP parallel directive, and inside that it should be inside the code block associated to the directive or inside that construct. And the clauses supported by the loop constructor: private, first private, we have discussed about the clauses. Reduction, we can do reduction using the loops also. Ordered, schedule. In this schedule I told you. So, if we see ordered, if we go back to the previous slide, we can see that these outputs are not in order. So, 0 iteration 1 and 2 is written first, then 7 8, then 3 4, then 5 6. Here 1 2, again 3 7 8 3 4 5 6. It is not written 1 2 3 4 5 6 7 8. It is randomly written by the threads. And now, if we call the ordered, put the ordered clause here, they will be written in an order. But why? How can they be written in order if there are multiple processors and each of the processor is executing one of the threads? This processor can work with their own latency and they can write in any order. You can, so you need a synchronization in between them. That means first the thread 0 will write, then the processor, so in thread 1 will write, so on. So there will be some sequentiality. This synchronization requires some sequentiality of execution of this, and that will also add to the overhead. So when we call put this ordered, there is certain overhead. And another point we have seen, there is an implicit barrier after the threads. That means there is already some synchronization, that unless all threads finish their work, the threads who have finished their work, they have to wait. In case we do not want that synchronization, because synchronization means wait time for certain threads, it means latency, it means overhead, we can use the clause no wait, that the threads will not wait for other threads to finish the work and start working on. Therefore, in this particular case, because they are operating on a thread private variable, this could easily have been done. We could have put no wait, and if you execute the program, you will see that the program speed is faster, because threads are not waiting, they are finishing their job and going to the next step as and when done. The other important construct is section construct. When there are not a do loop, but there are multiple sections of the job which are independent tasks, and they can be assigned to different processors or different threads. So, section construct divide the jobs into multiple sections and ask different processors to work in different section, and therefore the different subroutines or functions can be called in parallel. Different parts of the program which has no dependency among them can be executed in parallel. So, it is like hash pragma OMP sections is again a C construct, then you put hash pragma section and put a section there, hash pragma OMP section and put another part of the job there. So, these two parts will be concurrently or parallelly executed. So, if you write pragma OMP parallel and then pragma OMP section, pragma OMP sections and then pragma OMP section one part, pragma OMP another section another structured block, these two blocks of the codes will be executed in parallel. Or again this entire construct which is inside pragma OMP sections must be part of a construct pragma OMP parallel, because unless you say that this is already a parallel region using pragma OMP parallel, multiple threads are not launched. Once multiple threads are launched through pragma OMP sections, you can ask different sections will be executed by different threads in parallel. So, this is a way in which you can call different functions also, or different subroutines can be called, which can act independently, and they can be called in parallel. So, again pragma OMP parallel launches the parallel section, launches the parallel construct. Inside the parallel construct you have to use pragma OMP sections. That means multiple threads will be taking care of different part of the code block, and each pragma OMP section, each of the subroutine or the code block, you can also use write some part of the code, will be executed by different threads. This is a important this is very important construct. In a case you are not working on a do loop, or you are not working on a strict SIMD architecture where same instruction is being operated over different parts of the data, but you want to do an MIMD type of architecture. There will be different data and different instructions will be processed in parallel. The OMP section is a very useful construct. And again, here you also need not to worry about how the threads will be mapped, which thread will pick up which part of the sections, etc. OMP will automatically pick up one section and assign a thread for that, pick up another section and assign another thread for that. So, this optimization is as well as the load balancing is automatically done. And the clauses are private, first private, last private. Thread private is, we can see, is not supported here because this is not do loop. These are different data which each processor is working on. These are different instructions also. So, if we call the sections next time, this is there is probably nothing which is specific to a thread as a private variable and go with that thread again. Yes. Well, reduction, no wait, etc. Now, we have seen that section and for, they are called inside a parallel block. They have no utility outside the parallel block, outside a parallel construct, because these constructs are by definition part of parallel constructs. Only when parallel construct is launched, multiple threads are launched, you can do a hash pragma OMP for, or you can write hash pragma OMP sections. You can execute threads parallelly for you can execute the threads for parallelization of a for loop or for a section block only when it's already these threads are available, already it's a part of parallel construct. So, combined work sharing constructs are there which says that okay, for is always parallel for, there is no non-parallel for. So, in certain case, if there is only one for loop inside one particular parallel construct, you use hash pragma OMP parallel for, or if there is only one sections loop inside one parallel section, you use hash pragma OMP parallel sections. But if there are multiple parallel regions inside one parallel construct, you cannot use that, but in other case they save they make the programming simple. Another very important clause is reduction clause. Reduction is an optimized construct for doing parallelized repeating operation on a shared variable, and it is often required. We will see an example later that one particular shared variable is there, some summation, multiple threads are trying to do summation of something, some data, and everybody is getting its local sum, and finally this local sum sums to ensemble and a global sum has to be obtained, or you need to find out maximum of a large number of integers, and many threads are given and they are looking into certain part of the do loop, some of the numbers they are taking and trying to find out what is the local maximum. Finally, you need to get a global maximum. So, there are many cases when you need to find a global value, but you are trying to do it over many small local values, and reduction is the clause when this operation that you have a shared memory variable, you are trying to find out maxima or addition or something on that shared memory variable and doing basically same operations by all the threads on that data on that shared variable. And the optimized way to do it, because it is a shared memory access variable which is being accessed by multiple threads, there can be contention, there can be race conditions, there can be false sharing. So, to establish cache coherency, there will be certain latency in the threads also. To do it in an optimized way, reduction clause is important. It is a very important clause. We will see some of the examples later. Sorry. OpenMP provides reduction clause for specifying calculations involving mathematically associative and commutative operators so that they can be performed in parallel without code modification. So, we will see some of the examples later. The programmer must identify the operations and the variables that will hold the result variables, and the rest will be done by the compiler. Say you need to find out the sum. Programmer has to find out that the operation is sum and the summed variable is say total. The sum after the summation it will be written in a variable named total and the operation is sum, and specify that there is a reduction operation by all the threads and the local totals will be added to the final total through the sum operation. Compiler will take care of the rest. Compiler will divide it among threads, get the local values, sum it up. The result, again result has to be always a shared variable. The idea of reduction is that the same shared memory variable is being calculated by multiple processors through same operations. That means, if I say the variable total, it is sum of some variables, it is not sum of some variables and multiplication of some other variables. It is sum of some variables, and this summation process is over a large number of integers which is given distributed among different threads. Reduction is taking care of the summation. It is advisable to use reduction clause manually instead of doing it in the code, because this is optimized call avoiding false sharing and rest condition, because it is a shared memory variable and this shared memory variable is coming from several private variables which are doing the local sums or local maxima or local multiplication, and then finally ensembling everything, bringing them together and getting the shared variable. So, manually it can also be done, that you get all the local sums and you write that the global sum is sum of these local sums. However, if you try to do manually, because it is shared memory variable accessed by all the processors, it can give you some of the issues related to the cache memory, and therefore it is advisable that instead of doing it manually, instead of writing a code for taking local sums and finding global sum, is not specifically sum, it can be different procedure. We will see some of the procedures later. Use a reduction operation. The syntax is you just write reduction and then the operator name or the intrinsic procedure name. Operator is summation, multiplication type of things, and the intrinsic procedure is maxima, minima, average. Average is again summation, maxima, minima type of things, and then list which variables are which are the variables, what is the array that has to be taken for the reduction operation. So, one of this pragma WMP for default shared, and in this for loop sums all the, this will be AI, sorry, sums all the variable in the A matrix. There is a array A, there is an array A, and summation of all the arrays will all the elements of array will give you sum. So, sum plus is equal to AI is the for loop, and you write reduction. So, if we just write this, each thread will try to find its own sum, and then we have to do something, because they are trying to, all threads will try to write to the same shared memory location, we have to do something to take care of that. But if you just say that because multiple threads are doing this sum, this is a reduction operation with addition of the data of AI, multiple threads are doing AI, and the output variable is sum, then this is already taken care of. In Fortran also shared its result, all the variables are writing result is equal to result plus AI. So, all the elements of the matrix AI is written as summed up and result, and this do loop is parallelized. It is parallelization of the do loop, but this is operating over the same variable and doing basically addition. So, reduction plus result, that will take care of it. Many of the scientific computing calculations require this type of work, that distribute data in different chunks, ask threads to find the local minimum, maximum, sum, etc., and then find the global value. Reduction is of great use in these computations. We can see that if we have to find out maximum of n numbers, and each processor gets, there are n by np processors. So, each processor has one thread which gets n by np numbers and finds their local maxima, and then all these local maxima are taken care by one of the processor, and it finds the local global maxima of all the local maxima. So, this operation can be easily done by a reduction operation, that x is maxima of x data I. This is find out maxima in case it is a single processor thread, single processor execution. In multiprocessor execution, write that it is pragma OMP parallel for, and this pragma OMP parallel for has the clause that it is find out maxima. This is an intrinsic operation of the variable x. It is finding out, it is doing a maximum of maxima operations, find out maximum of certain variable and writing it in the location x. So, you will get the output this. This is extremely useful in many operations, we will see some examples later. Reductions clause specifies operation and a list of variables. OpenMP, when reduction is done, so you have to specify which operator has to be, which operator will be active and what are the variables on which it will work. When you have to use a reduction operation, OpenMP compiler first creates a local copy for each reduction variable, initialized to the operator's identity, say 0 for sum. If it is 0, it starts with sum, it starts with 0. If it is multiplication, it starts with 1. If it is finding out minima, it gives a large number and then finds what is the minima. So, this is basically how you do the sum or find minima. In a single processor reduction, ask all the processors to get a local copy of these variables, initialized variable, and then after work shared loop completes, all local variables have their local output, and this combines with the entry value and goes to the shared variable, and the final result obtained by combining all the variables and placed in the shared variable. Compiler level optimization is there, which takes care of the contention reducing and false sharing, and in next lecture we will see an example. And from up before OpenMP 4.0, there are for certain operations only reduction was allowed, but now user defined functions in reduction are also supported. You can say that this type of function I want to operate in a reduction mode, that all the threads will perform this operation and then their results will be taken in taken care of by master thread, and the same operation will be executed over the results of all the threads, over all the local results. You can do it in your customized way from OpenMP 4.0. Well, another important clause is schedule clause. Schedule clause determines how iterations will be mapped to threads. And in case we have large number of iterations, we have seen that OpenMP does some mapping. OpenMP distributes some of the iterations to some of the threads in a load balanced way. But if you need to have, there are large number of threads and OpenMP can result in uneven distribution and you need to control it, you can use shared variables. Pragma OMP parallel for schedule static is one way of using that, and then the next is followed chunk size. So, once this is static schedule, there are fixed chunks of iterations assigned to all the threads, and typically default, if you do not specify anything, the total number of iterations divided by total number of threads, that will be the chunk sizes. We can see some examples. In case we have 64 iterations using 4 threads, we say that pragma OMP schedule static, we do not specify any chunk size. 16 will go to each of the thread. In case we say that schedule static chunk size 4, so first 4 will go to thread 1, next 4 will go to thread 2, next 4 will go to thread 3, sorry, thread 0, thread 1, thread 2, thread 3, and then there will be some cyclic distribution of the threads. It is not first 16 will go to thread 0, first 4 will go to thread 0, then 5 to 8 will go to thread 1, so on. In case we use chunk size 1, it is really a cyclic distribution. 1 to 16 will go to thread 0 to 15, then 17 to 32 will go to thread, again go to thread 0 to 15, so on. So, there is a cyclic distribution of iterations, which is sometimes important, especially if we want to avoid some race condition and sharing of data by the threads. Well, this is default chunk size 4, it is shown here, chunk size again. So, up to this is the distribution we have discussed, and chunk 1 gives complete cyclic distribution. There are other parts of the schedule clause, pragma OMP parallel schedule dynamic, which dynamically allocates the threads, and each thread grabs some of the chunk size, and depending on what is the workload, it dynamically associates allocates the thread. But as it is doing it runtime and dynamically, there are certain cases when at every iteration you need to reallocate the number of threads, and there is some associated overhead. The other way is pragma schedule guided, where initially some of the blocks are given to some of the threads, and then it keeps on reducing the number of, because you got reduced number of threads after you initially assign some thread to some block, you start distributing them. The guided and dynamic has one good advantage, that they take care of the resource you are actually using. That means, if you are using some machine where some of the nodes are occupied by some other job, static will still give number of iterations, assign some number of iterations to those nodes. However, schedule and dynamic can understand that there is some extra loading on these nodes and put some of the jobs in some other nodes. And there is a runtime which looks into environment variables, and runtime associates the job. There are some examples, like in case of schedule static 2, there are 12 iterations to be distributed in 3 threads. Each thread gets uniform amount of work, and if this is static 2, that means 0 and 1 goes to thread 0, 2 and 3 goes to thread 1, sorry, 4 and 5 goes to thread 2. Then we can see that 6 and 7 again goes to thread 0, 8, 9 again goes to thread 1, 10, 11 again goes to thread 2. In case of cyclic distribution static 1, we can see 0 goes to 0, then 1 goes to 1, 2 goes to 2, 3 again goes to 0, 4 again goes to 1. So, there is a cyclic distribution of the threads. There is no chunk going to any of the thread. One thread, iteration to one thread, another iteration to next thread, the subsequent iteration to next thread, and so on. Also, we can see dynamic and schedule distribution, that there is actually uneven distribution if we use dynamic and guided commands, and in guided it is more uneven, in dynamic it is less uneven. They are trying to estimate what are the loads on different processors and allocating the threads accordingly. And in guided, it makes chunks of 2 and distributes it to different threads. In dynamic, in guided, minimum 2, it is assured that minimum 2 threads will go to minimum 2 iterations will go to one thread, but there can be different number of iterations. 3 iterations are going to this thread, different number of iterations going to thread. They do not assure load balancing in a method bookkeeping sense, but they assure load balancing looking into the hardware capacity of different systems. So, there is another thing called nested parallelism, calling parallel region within a parallel region. That means one thread will be there, it will be multiple threads will be there, and the threads are further launching sub threads. And this has to be done by set by a parallel environment. Nested environment has to be set by OpenMP set nested. And then we can see that first there are threads launched, which will launch inside a parallel construct. Threads will write their own ID, and then there will be another parallel section within the parallel construct. This is a parallel construct, within the parallel construct there is another parallel section. So, now each of the threads will become the master thread and launch the slave threads. So, thread 0 and thread 1 in the next section, thread which was the thread 1 in the first parallel construct, in the nested parallel section, it got a thread 0 number and it launched another thread. So, if there are multiple parallel loops, we can call nested parallelism and do that. In case we turn off the nested parallelism, this section is simply launched by they do not launch any further threads. They simply launch one thread in the nested parallelism. Multiple threads do not act there, but each thread again becomes a master in the nested parallel part. Whether it will be nested parallel or not, that has to be set up by the environment variable OpenMP set nested. If its clause is non-zero, it will be a nested parallel region. Nested parallel means there are multiple threads launched and each thread is further launching another set of threads. Okay. So, these are the references, and we looked into through these discussions directive constructs and clauses, recursion and scheduling clauses, and nested parallelism is introduced. We will see some important application of OpenMP program with a focus to critical issues in shared data handling. How if multiple threads are trying to write to a shared data, or which is often done in a practical scientific computing problem, how that is done by OpenMP based on the basics we have discussed so far. We will see it in the next class. Thanks.